Every iPhone in your pocket, every Tesla in a driveway, every F-35 fighter jet parked on a runway shares something almost nobody ever thinks about. Tucked inside each one is a tiny, incredibly powerful magnet, smaller than a coin in most cases, that makes the whole device actually function. Without it, the vibration motor in your phone doesn't buzz. The electric motor in a Tesla doesn't spin efficiently enough to be practical. The precision-guided systems in a fighter jet don't guide anything at all. Here's the part that should genuinely alarm anyone paying attention. One country controls somewhere around 94% of global production of these magnets. Not the raw ore, not just the mining, but the actual finished precision-manufactured magnets that go directly into the products. And over the past several weeks, that same country has tightened its grip even further, sending prices spiking and sending some of the biggest tech companies on the planet scrambling to lock down a backup supply before it's too late. This is the story of rare earth magnets, the material almost nobody outside a handful of industries had heard of a few years ago, and why Apple just quietly signed a $500 million deal that tells you everything about how nervous the situation has actually gotten. Let's start with the basics, because understanding why this matters means understanding exactly what these materials are and why nothing else can easily take their place. Rare earth elements are a group of 17 metallic elements sitting in an obscure corner of the periodic table, most of which the average person couldn't name if their life depended on it. Neodymium and praseodymium, usually combined into an alloy known as NdPr, are the two that matter most here. Processed correctly and combined with iron and boron, they form what's known as a sintered permanent magnet, and these particular magnets are, pound for pound, the strongest permanent magnets in commercial production anywhere today. That strength-to-size ratio is exactly why they've become genuinely irreplaceable across huge swaths of modern technology. Electric vehicle motors rely on them to generate enough torque from a compact, efficient package. Wind turbine generators rely on them to convert rotational motion into electricity without needing bulky, heavy alternative designs. Smartphones rely on them for speakers, vibration motors, and camera stabilization systems. And defense systems, from guided missiles to fighter jet components to precision radar, rely on them in ways most defense contractors would rather not discuss publicly in much detail. Here's the critical point that makes this whole story so consequential. There isn't a readily available substitute that matches their performance at a comparable cost. Engineers have spent years chasing alternatives, and while some progress has been made on shrinking how much rare earth material a given magnet needs, nobody has figured out how to simply eliminate the need for them in these high-performance applications. If you want an electric motor that's small, powerful, and efficient, rare earth magnets are, for now, basically the only realistic option at meaningful scale. Here's the number that should stop you cold. According to the International Energy Agency, China controls roughly 94% of global sintered permanent magnet production. Not a majority, not a dominant share, essentially the entire market. And it doesn't stop at the finished magnets. Research from the Center for Strategic and International Studies puts China's control at around 70% of global rare earth mining, roughly 90% of the separation and processing that turns raw ore into usable material, and about 93% of actual magnet manufacturing. At every single stage of the supply chain, from pulling the ore out of the ground to shipping a finished magnet ready to be installed inside a product, China sits at the center of nearly the whole global pipeline. This dominance didn't happen by accident, and it wasn't fast. It's the result of decades of sustained, deliberate industrial policy dating back to investments China made in the 1980s and 1990s, at a time when Western countries were largely walking away from rare earth mining and processing because of the genuinely nasty environmental costs involved. Processing rare earth ore is a messy, chemically intensive, environmentally damaging business involving toxic byproducts and, in some cases, low-level radioactive waste. Western mining companies increasingly decided it wasn't worth the environmental liability and regulatory headache, especially as prices stayed low for years on end. China, by contrast, made a strategic calculation to absorb those environmental costs in exchange for building overwhelming control over a material category that virtually every advanced technology on the planet would eventually depend on. Decades later, the result is a level of concentrated control over a single critical material category with almost no parallel anywhere else in the global economy. Oil, by comparison, is genuinely diversified, produced across dozens of countries with meaningfully different output levels. Rare earth magnets aren't diversified in any comparable sense. They're concentrated in one country to a degree that should make any government or company deeply dependent on them more than a little uneasy. This story isn't just historical background, though. It's actively escalating right now in ways that are showing up directly in real, verifiable pricing data. The NdPr alloy benchmark price hit $133.02 per kilogram on July 1st of this year, according to Shanghai Metals Market data. That's a jump of more than 21% in a single month, up from roughly $109.55 per kilogram just in June, a 21% price spike in 30 days, for a material that entire industries depend on and can't easily substitute away from, is not a minor market wobble. It's the kind of move that sends procurement teams at major manufacturers into genuine crisis mode. And the price spike isn't happening in a vacuum, separate from policy. Throughout June and July of this year, China has been actively widening its export control restrictions, expanding the list of specific U.S. and European firms subject to tighter licensing requirements on rare earth exports. This isn't a blanket ban across the board, it's a targeted tightening, giving Chinese authorities real leverage over exactly which companies in which countries can access these materials and under what conditions. For any company building products that depend on these magnets, that combination, rising prices layered on top of selectively applied export controls, creates a genuinely uncomfortable strategic position. You're dependent on a single supplier for a material you cannot function without, and that supplier has both the market power to raise your costs and the regulatory tools to potentially cut off your access entirely on a timeline largely outside your own control. This is exactly the backdrop against which Apple made a move that, on the surface, might look unusual for a consumer electronics company most people associate with phones and laptops, not industrial mining contracts. Back in July of last year, Apple signed a $500 million multi-year deal specifically to secure rare earth magnets manufactured domestically in the United States, sourced from MP Materials processing facility in Fort Worth, Texas. The deal included a $200 million upfront payment, a structure that, in supply chain terms, is essentially Apple paying a real premium to guarantee priority access and help fund the build-out of capacity that didn't fully exist yet. Tim Cook publicly framed the announcement as part of Apple's broader commitment to American manufacturing and its investment in the domestic economy, which is technically true, but also, once you look at the underlying numbers we just walked through, reads as something closer to a company recognizing a genuine strategic vulnerability and paying real money to reduce it before it turned into an even bigger problem. First shipments under the deal aren't even expected to begin until 2027, meaning Apple locked this in years ahead of actually needing the material. Exactly the kind of long lead time hedge you make when you're genuinely worried about a supply chain risk, not simply chasing good headlines. And Apple isn't uniquely exposed here either. Every major electric vehicle maker, Tesla included, faces essentially the same structural dependency. Every wind turbine manufacturer faces it. Every defense contractor building systems that rely on precision-guided components faces it too, which is exactly why rare earth supply security has increasingly become a topic showing up in defense policy discussions, not just corporate earnings calls. Here's the part of this story that's genuinely difficult and worth being honest about, rather than glossing over with easy optimism. Building an alternative, non-Chinese rare earth supply chain from scratch isn't a problem you can solve quickly, no matter how much capital gets thrown at it. Mining operations take years to permit and develop, particularly in countries with stricter environmental review processes than the ones China operated under during its initial build-out decades ago. Processing facilities, the step that turns raw ore into usable separated rare earth oxides, are even more specialized and even slower to build, requiring genuinely difficult chemical engineering expertise that simply doesn't exist at scale outside China right now. And magnet manufacturing itself, the final step, requires its own dedicated expertise and equipment that most Western manufacturers haven't maintained domestically for decades, precisely because it was cheaper and easier to just buy finished magnets from China. MP Materials, the company behind Apple's Fort Worth deal, represents genuine progress here, and it's worth taking seriously rather than brushing off. But realistically, it's also still a small fraction of the scale China currently operates at. Building a Western supply chain that can meaningfully rival China's 94% market share isn't a multi-year project. Realistically, it's closer to a multi-decade one, assuming the political and financial will to sustain that investment holds steady across multiple election cycles and corporate leadership changes, which is far from guaranteed. That's the uncomfortable reality underneath every headline about a Western company signing a new domestic rare earth supply deal. These deals are genuinely meaningful first steps. None of them individually is a solution to the underlying dependency problem, at least not on any timeline shorter than a decade or more. Zoom out, and this story connects directly to almost everything else happening across the US-China technology competition right now. Every conversation about chip export controls, about AI hardware restrictions, about who controls the next generation of computing infrastructure, tends to focus specifically on semiconductors. But rare earth magnets are a reminder that the technology supply chain has multiple genuinely critical choke points, not just one. You can have the most advanced chip design in the world, and it still needs to go inside a physical device that, in a huge number of cases, depends on a component China has near total control over. That hands China a form of leverage that operates completely independently from the chip war everyone's been focused on. Export controls on advanced lithography equipment or cutting-edge chip designs are a genuinely significant lever. But rare earth magnets represent a different kind of lever entirely, one that's arguably harder for Western countries to route around quickly, precisely because the physical mining and processing infrastructure takes so much longer to replicate than a factory retooling to produce a different chip design. This is exactly why you're starting to see rare earths show up more frequently in serious policy and defense conversations, not just industry trade publications. It's not really a niche material science story anymore. It's become a genuine strategic vulnerability sitting underneath a huge portion of Western advanced technology and defense manufacturing, hiding in plain sight inside products most people never think twice about. There's also a useful comparison here to how the semiconductor story unfolded over the past several years. A few years back, most people outside the industry had never heard of terms like EUV lithography or advanced node fabrication either. Now, those concepts show up regularly in mainstream news coverage because the strategic stakes became impossible to ignore. Rare earth magnets appear to be following a similar trajectory, moving from a genuinely obscure industrial topic towards something regular business and tech coverage increasingly treats as a first-tier strategic concern. That shift in public and policy attention tends to unlock more funding, more urgency, and more serious long-term planning than the issue got during the many quiet decades when China was steadily building its current dominance, largely unnoticed outside specialist industry circles. Let's spend a bit more time on the defense implications here because this part of the story tends to get mentioned briefly and then rushed past, even though it's arguably the most serious dimension of the entire issue. Modern military hardware is saturated with rare earth-dependent components in ways that go far beyond what most people would assume. Precision-guided missile systems rely on rare earth magnets in their guidance actuators. Fighter jets like the F-35 use hundreds of pounds of rare earth materials across their radar systems, electronic warfare components, and engines. Naval vessels, from submarines to destroyers, depend on rare earth magnets in sonar systems and electric propulsion components. Even something as seemingly mundane as night vision equipment and laser targeting systems relies on specialized rare earth compounds with no readily available substitute. This creates a genuinely uncomfortable strategic reality for defense planners in the United States and allied countries. In a scenario where geopolitical tensions escalated seriously enough that China chose to restrict rare earth exports specifically to defense contractors or to countries seen as adversarial, the impact wouldn't show up immediately. Existing stockpiles and already manufactured components would keep systems running in the short term, but over a span of months to a few years, depending on stockpile levels that vary significantly by country and by specific weapon system, production of new military hardware could genuinely slow or stall entirely, right at the moment that hardware might be needed most urgently. This is exactly why you've seen a noticeable uptick in Defense Department funding specifically earmarked for rare earth supply chain resilience over the past several years, along with government-backed investment in domestic processing capacity that goes beyond simple market incentives. When a supply chain vulnerability intersects directly with national security planning, governments tend to move with a different kind of urgency than pure market economics would otherwise produce, because the acceptable level of risk changes entirely once military readiness enters the equation. That's part of why this story, unlike a lot of purely commercial supply chain issues, has real staying power as a policy priority, regardless of which political party happens to be in power at any given moment. There's a third front in this story worth understanding, beyond simply mining more material domestically or signing supply deals with existing producers, the race to reduce how much virgin rare earth material is actually needed in the first place. Researchers across multiple countries have been chasing two parallel approaches. The first is recycling, extracting rare earth materials from products that have already reached the end of their usable life, like old electric motors, decommissioned wind turbines, and discarded electronics. In theory, this could eventually create a meaningful secondary supply stream that doesn't depend on new mining at all. In practice, rare earth recycling remains genuinely difficult and expensive with current technology because the magnets are typically bonded tightly into complex assemblies, making extraction a labor-intensive, chemically involved process that hasn't yet reached the cost efficiency needed to compete with freshly mined material at current prices. Some companies are making real progress here, and rising prices actually help the economics of recycling look more attractive over time, but it remains a genuinely small fraction of total supply today. The second approach is substitution, engineering motors and magnetic systems that need less rare earth material, or in some specialized cases, none at all. Several major automakers, including some working on next-generation electric vehicle platforms, have publicly discussed research into rare earth-reduced or rare earth-free motor designs, typically using alternative magnet chemistries or entirely different motor architectures like induction motors, which sacrifice some performance and efficiency in exchange for eliminating the rare earth dependency entirely. These approaches tend to involve real engineering trade-offs, often meaning a somewhat less efficient or more expensive motor in exchange for supply chain security, exactly the kind of trade-off that becomes more attractive to a company's engineering and procurement teams as rare earth prices keep climbing and export policy keeps tightening. Neither approach, recycling or substitution, is likely to fully solve the dependency problem on its own within the next several years, but taken together, alongside genuine new mining and processing investment happening in the United States, Australia, and a handful of other countries, they sketch the outline of a longer-term strategy that could meaningfully reduce, even if it doesn't eliminate, the current level of concentration in China's hands. It's a slow-moving, multi-pronged effort, and anyone expecting a fast, single fix is likely to be disappointed by how genuinely hard this particular supply chain problem turns out to be to solve. Here's my honest read on where this actually leaves things after digging through the numbers. I think Apple's $500 million deal is a smart, genuinely necessary hedge, but I also think it's important not to overstate what it actually accomplishes. $200 million up front and a multi-year commitment sounds substantial in isolation, but measured against a global supply chain where one country controls 94% of finished magnet production, it's a meaningful first step toward diversification, not anything close to independence. Apple, and every other major company dependent on these materials, is still fundamentally exposed to whatever pricing and export policy decisions get made in Beijing for at least the next several years, probably longer. What strikes me most about this story is how quietly it built up over decades before suddenly turning urgent. Nobody was paying close attention to rare earth mining policy in the 1990s because prices were low and the strategic consequences felt distant and theoretical. Now, 3 decades later, that early strategic patience has turned into almost complete leverage over a material category that modern technology and modern defense systems simply cannot function without. That's a pattern worth remembering, because it's exactly the kind of slow-building dependency that's easy to ignore right up until the moment it suddenly isn't. I'd also add this. It's tempting to frame this whole story as a simple case of Western companies and governments getting caught flat-footed by their own short-term thinking. And there's real truth in that framing. But it's worth remembering that the environmental costs China absorbed to build this dominance were genuinely severe, and Western countries walking away from that particular trade-off decades ago wasn't purely a failure of foresight. It reflected a real values-based choice about environmental regulation that most people would still defend today, even knowing what it eventually cost in terms of strategic dependency. That doesn't make the current vulnerability any less real or any less urgent to address, but it does complicate the simple version of this story where one side was just smarter than the other. Sometimes the trade-off between environmental responsibility and strategic self-sufficiency doesn't have a clean, easy answer, and I think that tension is worth sitting with, honestly, rather than papering over with hindsight. So here's what I want to know from you. Should Western governments be treating rare earth supply chains with the same level of seriousness, subsidy, and urgency as semiconductor supply chains? Or is this dependency simply the price of decades of cheaper materials, one that's not really worth the enormous cost of trying to fully reverse? I think there's a genuine, honest argument on both sides here. Drop your take in the comments below. I read every single one. If you want to keep following exactly how this rare earth story develops, along with every other major materials, chip, and manufacturing story shaping the US-China tech relationship, this is exactly what Eastern Engine covers every single week. Hit subscribe so you don't miss the next one, because between Apple, Tesla, and half the defense industry all quietly scrambling on the same issue, this story is genuinely far from finished. See you in the next video.